Last time we defined conditional probability, which was the probability of an event P given that an event A has occurred. We defined the formula probability of B given A is equal to probability of B intersection A divided by probability of A. One of the main ways to compute conditional probability is called the Bayes theorem, and we are going to talk about this today. But before we talk about Bayes theorem, let me ask you a question. Suppose there is a scientific theory which predicts that pretty soon there is going to be a solar eclipse. Let's fix a date. So say that it predicts that solar eclipse happens on 1st October. On this date, you go out, check, and indeed solar eclipse happens on that day. Let me be more precise. Say that it predicts with probability 0.8. So that means the scientific theory says that with probability 0.8 solar eclipse will happen on 1st October. You go out and see that the solar eclipse has happened. Question is, what is the probability that the theory is indeed correct? Looking at the first glance, you might say 0.8. You might also guess that that is not going to be correct. It is not going to be that easy. So let me say some reasons why this is definitely not correct. Think of a situation where almost all theories predict the solar eclipse on 1st October. So that means it was going to happen no matter what. Whatever be the scientific theory, it was predicted that the eclipse would have happened on 1st October. In that case, I can't take this as a very, very serious evidence. That means eclipse should not imply with high probability that the theory is correct. So in some sense, the Bayes probability of the eclipse happening on 1st October should also be important. Bayes probability of eclipse is pretty important. In other words, if the Bayes probability was 1, then it doesn't say anything about the theory. Other factor could be that probability of eclipse given theory is true. On the other hand, probability of eclipse given theory is not true. These two ratios should be pretty important. In other words, if the theory was not true, what would have been your probability? If this was given, then we should be able to estimate this probability. So the 0.8 guess definitely is not correct. It should depend on many other factors. What would we do? We'll fall back to the basics. In this case, remember, what is the question asked? Say A is the event that eclipse happens on such and such date. B is the event that the theory is correct. It is given that probability of A given B is 0.8. But what we are asked is probability of B given A. This is the question which we have to solve. Remember, the question is given probability of A given B, how to calculate P of B given A. And this is essentially Bayes theorem. So let us derive it. Probability of B given A by our formula is probability of B intersection A divided by P of A. Now we notice that probability of B intersection A can be written in these terms. Using the similar formula, again, I can write it. And this is what we know as Bayes' theorem. Actually, most of the time it is utilized by actually dividing this in two events B and B complement. What do I mean? Notice that I will just check the denominator. You remember the partition formula. Event A can be divided into two parts, or my whole sample space can be divided into two disjoint parts, B and B complement. So either A happens because B has happened, or A happens because B complement has happened. This is in some sense the working version of Bayes' theorem. This is what we use most of the time. The formula is not very difficult. I would just ask you to internalize it in the sense of how we derived it instead of actually rot learning the formula. Let's see a few applications. So the first example would be from the city of Mumbai. Let's say we have 90% black cabs in Mumbai and 10% white cabs, taxis which are running. It is known that white taxi drivers are rash. How do we know it? They are involved in 5 times more accidents than black cabs per cab, let's say. So normalized to the number, we know that a white cab is 5 times more likely to get into accident as compared to a black cab. You get to know that there has been an accident. Question is, what is the probability that the accident or the cab is white in the accident? Again, we will define our events and then it will be not very difficult to calculate the probability. Let's say CW is the event that car is white, CB is the event that car is black, and AB the event that accident happens. In this case, we want the probability that the car is white given that the accident has happened. Applying Bayes' theorem, this is probability that accident happened for a white car multiplied by white car, and then applying partition formula for the denominator of the Bayes theorem. In other words, to calculate probability of A, we just apply the partition formula. So we don't have all the quantities, but actually we have all the possible ratios. For example, we know that 9 out of the 10 cabs are black. Similarly, we know that probability of A given CW is 5 times probability of A given CB. That means a white cab is 5 times more likely to be involved in an accident. So that means you can say 5, 5 and 1. So this gives me 5 upon 5 plus 1 into 9. That is 5 by 14. So you see that even though a white car was much more probable to get into accident, still since the number of white cars is pretty low, this implies that the probability that car in accident is white is small. This keeps telling you that the base rate is very, very important. In this case, the base rate is the probability of the car being white or car being. Many a times we forget this formula. So this is one of the applications. Let's take one more. And this will come from something very pertinent to computer science and the hot topic, machine learning. Let's say you want to detect spam, so you want to create a spam detector for a particular person. Noticing the data for that particular person, you have observed few trends. So what are the trends? One, a non-spam mail has word money in it only 5% of the time. Second thing, spam email has money almost 50% of time. Makes sense. Third, that person has a good friend who uses money 40% of the time. In 40% of his emails, there's a word money. He's obsessed by money. Now, question would be that given an email has word money, what is the probability that it is spam? We will assume that the friend is a good friend, so we don't want to classify it as a spam. As soon as we say that, from the example above, you realize that the base rate is very, very important, and it means the frequency of non-spam emails, emails from the friend, spam emails, that's very, very important. So we will say that 10% of the emails come from the friend, rest equally are divided between spam and non-spam. So this is the frequency of emails of these three types. So there are three kind of emails. 45% of them are non-spam, but they contain money only 5% of the time. 45% of them are spam, they contain money 50% of the time. 10% of them are coming from the friend who uses money 40% of the time. Given this data, we have to find out what is the probability that something is a spam given it has word money in it. Let's define the events. S is the event that it is spam. N is the event that is non-spam. F is the event, it's a mail from a friend. So these are the only three possible. I want to club friend and non-spam together, but since the word money is used differently, so we will keep them as two different kind of email. So these are the three possible things. Either it comes from friends, it's a non-spam, or a spam. We want to find whether the word money occur in it or not. Actually, we want to find the opposite way. Given that money word has occurred in it, what is the probability that it is spam? We can apply Bayes' theorem again. It becomes probability of money given spam multiplied by probability of spam. And now the probability of money, P of M, can be divided into three parts. One is when it is coming from spam. One is when it is coming from non-spam. And the last one when it is coming from friend. You know all the relative frequencies, so exercise is to calculate this value. It's not a hard exercise, you just have to take the required ratios and you can figure out this. Let's talk about one more problem which we actually discussed in the introduction. This relates to the medical field and something which creates a lot of error even among experts and professionals in medical field. So let's say there is a test for cancer which is pretty accurate to 0.9 probability or same as 90%. So what does it mean? That if a person has cancer, this event is pretty rare. We will say that only 0.1% people have cancer. Even then, it reports 90% of the time that person has cancer. So 90% of the time it is correct on patients. On non-cancer people, I should say that the person does not have cancer. In this case, 90% of the time, it says no. That means person does not have cancer. So in both the cases, when the person has cancer or person does not have the cancer, test is accurate with 90%. Someone goes and gets the test. Test is positive. How worried you should be? In other words, what is the probability that the person has cancer? Before I solve this for you, I would like you to take a guess that if the test is accurate with 90% probability, what do you think the probability should be? Now you have made the guess. I assume you will stick by it. Let's calculate the probability using the form. I will use the event names, that is quite clear. So this is the probability of cancer and this is the probability that test is positive. So this is what we want to compute by Bayes theorem. This is the numerator and denominator will be the similar two terms. This is when the test is positive and this is when the test is negative. And applying these probabilities, we can calculate these. In this case, I have created a demo to show how these probabilities go down. Let us think of the case when the test is accurate with 0.9 probability. So probability of test being correct on cancer patients, it's 0.9. The next thing is probability of test being incorrect on non-cancer individuals. So that is only 0.1. And just to explain this graph, you should see that this is the fraction of people who have cancer. So at this point, 1 out of 2 to the power 5 people have cancer. So 1 out of 32 people have cancer. X-axis here 10, that means 1 out of around 1000 people have cancer. So when we said that only 0.1% people have cancer, that means this is where I want to look, and the probability is very, very close to 0.1. So you see that the test actually does not tell you anything. Even if it is positive, it is only telling you that the person might have cancer with probability 0.1. So the test has to be much, much more accurate if you believe that 1 out of 1000 people have cancer. Let's see how much. Let's make the test to be very, very accurate. It is 99% correct. Again, remember, this is the probability of test being incorrect on non-cancer individuals. So I will keep it 0.01. That means it is correct on non-cancer individuals with 99% probability. And you still see that at this point, when 1 out of 1000 people have cancer, still the person will have cancer is very, very low. It's just 0.15 or 0.12 or something. Even though the test was accurate 99% of the time. Let me make the test much more accurate. So now you see that when the test is that accurate, if 1 out of 1000 people have cancer, then the person who got tested has cancer only with probability 0.4 or something. Since cancer is not present with very, very high probability in the general population, only 1 in 1000 people have cancer, then for the test to be accurate, it has to be really, really accurate to make sense. Otherwise, it's only a small evidence and it should be backed by further data for some x-rays or something to say that the person has cancer. So this demo clearly shows the importance of Bayes rate. When 1 out of 32 people had cancer, then this test was really, really, really accurate. But you see that sharply as the fraction of people having cancer goes down, the test's accuracy also is going down. And this is the lesson you should learn from Bayes theorem. Thank you.